5 factors of soil formation and parent material. There's the climate, there is the topography, you have the biology of the system, and you also have time. So the idea of the exercise today really is to have a look at the soils along the classic Catena sequence in North Wales, which runs right from the coast here all the way up to the mountain tops. And essentially the Catena sequence is an altitudinal sequence of soils which, basically as you go up in altitude you have changes in climate but also changes in geology. So here we are, still in the Snowdonia National Park, and here we have another great soil order of the world. This one here is called a Spodosol, or also known as a podzol. It has an acidic parent material, so in this case we have a mixture of acid igneous rocks such as rhyolite, which break down really slowly, and we also have a sloping hillside. In terms of climate, we have a lot of rainfall, so we've got about 2,000 millimetres here, which is a net positive water balance. So we've always got water moving through the soil profile. And the combination of the sloping position, the fact that we've got low temperatures in the uplands, we've got large amounts of rainfall, and we've got slopes, and the acid igneous parent material means that this soil profile is particularly nutrient poor. And it has some classic features about it, which is we've got the diagnostic horizons for this podzolic soil, the Spodosol, which is the black organic horizon here. We've then got the leached horizon here, which you can see is a sort of a white colour, and then underneath here we have the mineral B horizon, which is enriched in iron oxides and hydroxides, and then underneath here, if we went down a bit further, we'd be able to find the C horizon, which would be the bedrock, which in this case is glacial till. So how do we get this soil type to form? Is this parent material, which is acid igneous, gives rise to this, it's a similar vegetation to which we had on for the histosol, which is Vaccinium myrtillus, mosses such as sphagnum moss, and heather, so Calluna vulgaris. That gives rise to litter, which in itself produces lots of organic acids, so things like citric acid, malic acid, etc. And when it decomposes, those organic acids, which are produced by the microorganisms when they break down this litter material here, the organic acids, which are negatively charged, pass through here into the start of the mineral layer here. So we have no mixing of these two horizons because there's no worms here. But as the organic acids are moving down here through this layer here, they're negatively charged. The iron 3+, so oxidized iron, is complex, so that's 3+. The organic acids like citrate are 3-. They bind together, and the ferric citrate is then transferred into this lower horizon, and ferric citrate is bright orange colour, a bit like the drink iron brew, and is reprecipitated here. So the microbes use the organic acids here and the iron drops off, and so you get the movement of iron from these upper horizons into the lower horizon to give it this sort of colour sequence of black organic matter, white leached horizon, and then the accumulation of the iron in the subsoil horizon. And that is the classic feature of a spodosol. Normally we'd expect this soil to be quite wet for large portions of the year. In terms of, it has quite a lot of moisture in it, even though the moisture is draining through the soil quite well. So in this soil we never see waterlogged conditions. We only ever see water moving progressively through the soil profile. And there's plenty of rain to be able to do that. So we'll put the theta probe in and see what it says. Okay, so this is saying that it's actually pretty wet here today. It has rained recently. It says it's 72% by volume moisture, which means that the soil here contains a large proportion of water, and the rest of it is just this organic matter here. And one of the classic features of this particular topsoil that we see is that if we took this and we put it in the oven, we would see that it would shrink massively from a sort of a volume like this, if we took a soil core, down to something like that. Because so much of this soil is made up of water, when you dry it, of course, it just shrinks. So it doesn't really surprise me. So one of the other classic things that we can do, of course, is measure the soil pH, because measuring the soil pH tells us a lot about the processes that are operating within the soil. So here we have the pH probe, and we can see that currently it's reading pH 3.94, which is, incredibly acidic really. It's similar to some of the other soils which we'll see higher up on the mountain. And what it's telling us is that all of the nutrient goodness has been washed out of this soil and basically been replaced with what we call the acidic cations. So we've lost all the sodium, potassium, calcium and magnesium, or a large proportion of it, because of the amount of leaching through the soil from the amount of excess water and the slope position. And what we've been left with is hydrogen ions and aluminium ions, and we can call those the acidic cations. And classically, the pH, if it's less than 4.5, it means that the organisms that live in this soil have to be super adapted. So it also means that we don't have any earthworms in this soil profile, because earthworms can't stand acid conditions. So we've lost them, we've lost the bioturbation that comes with this, and we start to see this distinct horizon banding in this soil due to the fact that the pH is really low. If we also look at the nutrient content of the soil, which we use electrical conductivity as a proxy for that, so the amount of ions that are in solution, we can see here's the electrical conductivity probe. If we put that in, we can see that the value is about 120 microsiemens per centimetre. So it's actually higher, slightly higher than I would have expected on a normal day. With looking at values around 80. But it is the summer, maybe we've had a little bit more organic matter decomposition and a few more ions in solution, but generally it's pretty low. So, and it's well beneath the threshold of about 3 millisiemens per centimetre, or 3,000 microsiemens per centimetre, that would be indicating of salt toxicity, for example. So it does indicate that it's really low nutrient content in this particular soil. If we looked down into the soil profile, probably what we would find is that in these horizons, the lower horizons, the pH would be slightly higher, because of course the nutrients are washing down from the top where all this acidity is that's being generated, and a lot of them are being redeposited here or washed out completely down the slope. So the pH does tend to be slightly higher here, probably into the 4.7s, and the electrical conductivity will be slightly higher because up here we have pretty much solid organic matter. Then we have this mineral boundary here, and this is all of the parent material that is weathered away into this material here, which contains a mixture of sand, silt and clay. It's like a sandy loam texture here, and the clays will be retaining some of those nutrient cations in the soil profile. So it's, a lot of the nutrients may be retained here, but a lot of them will be washed out.